Welcome to The Explainer. Today, we're jumping right into the core of physics to get a handle on something we see all day, every day, but maybe don't think about too much: motion. We're going to break down the basic rules that control how everything moves, from a bird flying around to a car driving down the street.
Okay, this seems like a super simple question, right? A bird is obviously moving. But what about that person on the bus with you? It's a tricky one, and the answer actually unlocks a huge idea in physics. So let's ask it again. Is that person really moving?
All right, here's our game plan. First, we'll solve that bus puzzle. Then we'll build up all the key terms you need to describe a journey. And finally, we'll see how scientists can literally draw a picture of motion using a simple graph. Let's get into it.
First things first, let's get to the bottom of this bus mystery. Figuring this out is the absolute key to understanding the whole concept of what we call relative motion.
So here's the secret. An object is only in motion when you compare it to something else. We call that something else a reference point. So compared to the seat you're both sitting on, the person next to you isn't moving at all. But compared to someone standing on the sidewalk watching the bus go by, yeah, you're both moving pretty fast. It's all about your point of view. It's all relative.
Okay, so we've settled that motion is relative. The next question is, how do we actually measure it? Well, it turns out physics has two really different ways to talk about how far something has gone.
This little story about two students, Sheetal and Prashant, explains it perfectly. See, Sheetal takes the long way. She walks from her house to her friend Sangeeta's house, and then they go to school together. Prashant, though, he just goes straight from his house to school. They start in the same neighborhood and end up at the same school, but their trips are totally different.
Now, distance is what it sounds like. It's the total ground you covered. It's literally every step Sheetal took. So you take the 500 meters to Sangeeta's place, and you add the 1,200 meters from there to school. All told, she walked a distance of 1,700 meters.
Displacement, on the other hand, does not care about your scenic route. It's the as-the-crow-flies measurement. It's just the shortest, straightest line from your starting point to your finishing point. In our story, that's Prashant's path, a straight shot of only 1,300 meters.
And get this leads to a really wild idea. Think about a marathon runner. They run a huge distance, right? Over 42 kilometers. But if their race finishes at the very same spot where it started, their total displacement is a big fat zero. Why? Because they ended up right back where they began.
So we've nailed down how far with distance and displacement. The next obvious question is how fast. And you guessed it, just like before, physics has two different ways to answer. And it all comes back to the difference between the winding path and the straight line.
This table breaks it down nicely. Speed is the one we use all the time. It's just the total distance you went divided by how long it took you. Velocity, though, is your displacement divided by time. It only cares about how quickly you got from your start to your finish in a straight line. And crucially, it also includes your direction.
And this is a really big deal. It means you can have a constant speed, but your velocity can be changing the whole time. Just picture a race car on a circular track. Its speedometer might be stuck on 150 kilometers per hour. That's a constant speed. But since it's constantly turning, its direction is constantly changing. And if your direction is changing, your velocity is changing too.
Okay, we've got speed, we've got velocity. But what's the word for when your velocity itself is changing? Well, that brings us to our next major idea: acceleration.
Let's look at this little road trip. We've got three friends, Amar, Akbar, and Anthony. Every 30 minutes, Amar covers a steady 20 kilometers. He's consistent. But look at Akbar and Anthony. The distance they cover every half hour is all over the map. Their movement is choppy and uneven.
This difference gives us two basic types of motion. Amar's steady pace is called uniform motion. Akbar and Anthony, on the other hand, are in non-uniform motion. Think of a car in city traffic, always speeding up and slowing down. It's this non-uniform motion that is the key to understanding acceleration.
Now, the most important thing to get here is that acceleration is any change in velocity. We usually think of acceleration as just speeding up, hitting the gas. But in physics, it's more than that. Slamming on the brakes is also acceleration. It's just negative acceleration. And remember that race car? Even turning a corner at a constant speed is a form of acceleration because you're changing your direction, which means you're changing your velocity.
All right, for our last section, let's put all of this together. We're going to see how physicists take all these ideas, distance, time, velocity, acceleration, and use them to create a simple but really powerful picture of a journey, a graph. So when you plot the distance an object travels against time, if that object is in uniform motion, like our steady driver MR, you get a perfect straight line going up. And the steepness of that line, its slope, tells you exactly how fast it's going. A steeper line means a higher speed. Simple as that.
But if the object is in non-uniform motion, the graph looks totally different. Instead of a straight line, you get a curve. That curve is a picture of the object's speed changing over time. It's a visual way to see it either speeding up or slowing down.
Now this graph shows us what steady, constant acceleration looks like. But notice, this time we're graphing velocity versus time. And here, a straight sloped line means that the object's velocity is increasing by the exact same amount every single second. It's the signature look of perfectly smooth acceleration. So there you have it. We've just built an entire toolkit for describing any journey, from figuring out if something's moving at all, to displacement, velocity, and acceleration. We can now chart and graph any kind of motion. If you want to keep exploring these ideas and see how they connect, definitely make sure you subscribe to the A1 Institute YouTube channel. But all this learning leaves us with one giant new question. What actually causes motion? What is the push or the pull that makes things start, stop, or change direction? Well, that's a story for another time.